This call is now being recorded.
Okay, so today we are going to learn a new classification technique, that is k nearest neighbors. In the same way, like we already know how to import the modules and all, right? So we'll take a data set and we will see how the code of KNN works and all, and how the classification algorithm prediction is going on in the k nearest neighbors. Clear? Okay. Let us check. Let us check the flow of the KNN, how it does the predictions and all, and then we'll go with the code. Okay, so before KNN, suppose think like this. We have x1 and x-axis and y-axis, that is x1 and x2, and we have category 1 and category 2. Think like category 1 is in red in color and category 2 is in green color. What happens if a new data point, the gray color, the plus gray color has come in picture? And how does it decide whether it belongs to this green group or red group? I mean, whether it belongs to 0 category or 1 category. How it decides? So before KNN, this is the problem statement we are having. But after applying the KNN, so the full form of KNN is k nearest neighbors. Okay, so it's a k nearest neighbors. That means nearest neighbors. It checks the nearest neighbors through some mathematical formula, and it identifies which neighbor is near, and then it assigns that new data point to those categories. Okay, let us see how this works and all. Okay, see, before KNN, this is the new data point which we have, but after applying the KNN, so think like this, the entire data set is passed into this KNN filter kind of. Once the KNN filter does the job, this is the output after the KNN, after KNN is applied on the data set. That means it has chosen that new data point belongs to this red category, that is category 1. But how did it choose? That's the main question. How did it choose? Okay, these are the steps actually. So choose the number k of neighbors. Okay, we need to select like how many neighbors you want to proceed with, like how many data points you want to search for. Like if you want 5 neighbors or 6 neighbors, you need to how many neighbors you want to attach with the new data point. We need to decide. Okay, take the k nearest neighbors of the new data point according to the Euclidean distance. Okay, how do you identify distance between the points in a graph, like in a Cartesian plane and all? It's through Euclidean distance. Then there are so many distances out there. We have so many geometrical distances out there. But out of all, we are taking this Euclidean distance. That means we are able to identify the distance between one data point to other data point by using this Euclidean distance formula. Okay, if you are suppose think like this. So if I'm taking 3 neighbors, take some like randomly 3 neighbors. If I'm taking 3 neighbors, so if a new data point has come in the plane, xy plane. So through the Euclidean distance, it identifies the first 3 category 1 data points, the distance to the new data point, which is the shortest distance of the first 3 data points of the category 1, and it identifies the distance of the category 2 as well. And if the category 1 has less distance compared with category 2 to the new data point, that new data point is added to the category 1. So that's how the KNN works. So that's how k nearest neighbors works. You need to choose the neighbors, and then you can identify the distance between the data points by using the Euclidean distance. The shorter the distance, the data point goes into that particular group. Okay, among these k neighbors, count the number of data points in each category. Count the number of data points in each category. Let us see. Assign the new data point to the category where you counted the most neighbors. Okay, let's see. Let's go here. Choose the number k of neighbors as k is equals to 5. Okay, we'll choose 1, 2, 3, 4, 5. Right? So this is 3 and this is 4 and 5. So if you draw a circle like this, so 3 points are the closest one compared with these 2 points, right? Compared with these 2 points. That means there are three points. I mean, the majority of category 1 is 3. Always take odd number as neighbors, because odd numbers, if you take even numbers, think like this. If the distance is same of green and red, then it becomes very difficult to the machine to like judge to which category it belongs. So take a odd number always. Okay, so this is the Euclidean distance formula. Think like this. We have x1, y1, that is p1 of x1, y1 and p2 of x2, y2. If you want to find the distance between this p1 and p2, the formula for Euclidean distance is under root of x2 minus x1 whole square plus y2 minus y1 whole square. Okay, yeah, same. Think like this. From here, whatever the shorter distance, like the maximum 5 points distances are there, you'll calculate those 5. Think like this. We have 2 green points and 3 red points. So if you draw a circle among these all data points, the 3 data points are more compared with 2 green points, right? 3 red points or more. So this value will be pushed into this category 1. That's how the KNN does the prediction. Okay, check this out. So take step 2. Take the first step. First step is choose the number of k of neighbors that we have chosen randomly, that is 5. Take the k nearest neighbors of the new data point according to the Euclidean distance. Okay, here is my data point. Through the Euclidean distance, if I identify it, see. So these are the points which have the nearest Euclidean distance for this actual data point. That is a new data point. So we have 3 and we have 2. Okay, we have 3 and we have 2. Good. So now, see, count the category. Category 1 has 3 neighbors and category 2 has 2 neighbors. So that's why this data point will be assigned into this category 1. Is that clear?
Yes, sir.
I hope it's clear. Yeah, good.
Yes, sir.
Yeah. So now we'll check the code. As you know, like already we have done the Python code and everything. I'm already having the code. I'll just show you the code and we'll check how the code works and all, and we'll proceed further. Okay. Okay. Let's start with classification, and we have k nearest neighbors. I'll go into this k nearest neighbors. Okay. KNN.py. Good. Okay, and then this also k nearest neighbors. Perfect. Done. So we have chosen our project directory to the k nearest neighbors, where our data set is actually present. Okay, first we need to import the libraries. The first step, importing the libraries is done, and importing the data set. Social network ads. Yeah. So I guess yesterday we have seen this, the same thing, like the user ID, gender, age, estimated salary, and purchase. Like, what is the probability that whether a particular user is going to take that offer or not, or he or she is going to purchase the product or not. That is our problem statement. Nice. So we have this age and estimated salary. We found out that age and estimated salary are highly correlated with the purchased column, and the user ID, gender are not that much correlated. It's not that correlated. So we are going to ignore these 2 columns. So we are taking the age and estimated salary as our inputs and purchased as the output. Clear? Yeah. So first we need to select the inputs. That is the age and estimated salary. It's done. And yeah, so we have chosen the output as well. Now the next step is we need to split the entire data set into train test split. Okay, again, I'm telling you why we need to divide the entire data set in train test is after training, you need to know how the performance of the model, right? So in order to know the performance, you need to test the results, because we'll have the actual values and we'll have the predicted values. Based upon those actual and predicted values, we are going to perform our analysis. Yeah, clear. So now if I go here, yeah. Okay, so no cross validation. So it's the whole code actually. Model selection, I'm going to use it. Yeah, I'll use model selection. Yeah, it's done. And here it's done. And since age and estimated salary are like, I mean, I told you, like age is a smaller number compared with estimated salary. So being a machine, what it does is it ignores the small values because it can't identify the smaller value when the larger value is present. So we need to bring that to the same scale. For that, we will do the feature scaling process. That is nothing but in the statistics we are seeing standard normal distribution, right? In the same way, feature scaling is one technique. Okay, I'm going to apply our feature scaling. Yeah, we already know, like for applying any transformation techniques in the machine learning, first we'll create a mask for it. That is an object we'll create, and then we'll apply that mask on top of the data set, and we superimpose that so that it performs that particular task. Okay, I applied my feature scaling, and X-train and X-test are ready. Okay, now fitting the KNN. Okay, from sklearn.neighbors. So in this neighbors, you'll find this k neighbors classifier. K neighbors classifier. Okay. Okay. See, in the k neighbors classifier, we are using n neighbors as 5 and metric. So metrics, they have the people who have designed KNN has designed like few metrics actually. So Minkowski, if you use it, it takes the Euclidean distance actually. So depending upon what metric it needs to identify. So based upon that, it takes the Euclidean distance actually. So the classifier is ready now. Now I'm going to apply classifier.fit. Okay, our k neighbors classifier is ready. Yeah, it's done. So now we have X test. Directly, I'm going to perform my prediction on the X test. Ypred. We have Ypred. Yeah, the predicted values which has come out from my KNN, that is k-nearest neighbors classifier. Right? Yeah, we done. And if you take y-test, we'll just compare the results. Okay, see, we'll just compare the results. Okay, see, yeah, this is y-pred and this is y-actual. Left side is y-actual, y-test. The right side we have is the y-pred for that y-test. Yeah, okay, we got few values. So in order to, we can't check it manually, right? Since there are so many rows out there. So we'll use confusion matrix to evaluate our model. Right? To evaluate our model, we use the confusion matrix. Okay, I've used CM. If I open up CM, see, so these are the.
Sir,
yeah.
Sir, what difference between white train and white text, sir?
Okay,
White
it's the
text
actual
means
data set
after
only. We are
predicted the
dividing that
values.
into. No. So it's the actual data set only. So it's a completely, it's a Y. So inside that Y, we are like dividing the data set into train and test. So train will have 80% of the data points of the original data set, and test will have 20% of the data points of the original data set. 25. So 25%. That means 75% is the original and 25% is the test set. Is that clear?
Okay, sir.
Okay. See now. So we have the true negatives we have and the true positives we have. Right? Yeah. So in order to find the accuracy, how accurate it is, that is 64 plus 29 divided by total. So first we'll identify the total. That is 64 plus 4 is 68. 29 plus 3 is 32. Total 100. So out of 100, what 64 plus 29 divided by 100? Right? 64 plus 29 is 93. 93 divided by 100. 0.93. Do you remember in the logistic regression curve, we got like 89% the accuracy, if you remember. Right? Okay, we'll check that as well because yeah, so we need to check that accuracy as well to compare the models. We'll just have a look at it, the logistic regressor as well. Okay, this is the same data set only. What we're going to apply is we'll apply till confusion matrix. Okay, and then if we check the CMs, 65 plus 24. So that is 89. 89 divided by 100 is 0.89. So we have 89% accurate logistic regression model. If you apply k-nearest neighbors to the data set, it has given us 93% accurate model. 93% accurate model, right? So if you apply our visualization techniques, like by taking the listed color map present in the map plotted library, if you apply it, check the plots. See, so this is the plot now. So this is the training set. So inside the training set, no. So see, the red zone is the category 1 and the green zone is the category 2. Okay, so the entire prediction is done with a line in between it. And this line, you know, to the left of this line belongs to category 1, to the right side of this line belongs to category 2. So that's how the training is done. And when you applied that on the test set, yeah, that was good. Only one red data point was going into this category 1 and few green data points was going into this category 2. Think like this: category 1, category 2, that is 0. Category 1 has 1, the green. So which is good. I mean, to the green zone and the red zone, if you apply the matplotted library, we can clearly see the test set was performing well, and hence we go with the KNN module till now. If we with the logistic regression is giving us 89 and KNN is giving us 93%, right? So that's why we can assume that KNN is the best suited model for this data set till now, so far. So that's how, you know, the KNN is done internally in the backend. What are the steps I told you? It is done in the backend, and in the front end, like to check the visualization of the graph and all. These are the techniques to visualize your graphs. Okay. Yeah, that's it for KNN. And now we'll enter into our decision tree. Okay. As we have already seen decision tree in the regressor curve. If you remember in the regression, we have already seen the decision tree there. Yeah. So decision tree we have already seen. I told you like decision tree is used for both regression as well as classification purposes. Okay. So that's why it is called as CART. Classification trees can also be done by using decision trees, and regression technique is also done by using the decision trees. So think like this. So we have the data points in this manner. So green belongs to 1 category, red belongs to 0 category. Okay. What decision tree does is it divides the entire this thing into groups, I told you, based upon the amount of information. Think like this. If you consider this group, the green data points, if you apply to the center, this has the maximum information to this block. So it does a split here, one split, and to this here, one more split, and we have one more split here. This red belongs to one split, and this has maximum information. This is one split, and this is one split. So entirely the decision tree does this kind of splits here. See, the split one is done like this. When the split one is done, it divides this data set and this data points. And the split two is done like this. It divides this into this. So how many splits it is going to do? Like till the last point where it identifies the least information is there inside the data points. Till then, it does this split operation. Right. Suppose, for example, if a new data point has come in picture. So the decision tree, what it does is it takes decisions in the format of if loops. If you remember, if elif, we have done that in Python, right? For example, if the data point is in between, consider like this, like 75 or something, 75. So think like this: towards left side of the 70, it doesn't go. So that's a no. After towards the right side of 70, it goes here, and above here, you'll check this axis now. To the 60, above 60, it takes into picture, and after that, the 75 point, whatever it is that it assigns into this group, this red group. So according to the number or the position of the data point, according to the information it has, it directly assigns itself into the particular batch. And that batch, if it is a category 1 batch, it assigns that new value to be as a category 1 batch. If the data point is entering into the category 2 batch, new data point, if it is entering into the category 2 batch, and it assigns that in the format of a category 2 batch only, the green data point, right? Okay, we'll see the code now. We'll see the code for our decision tree. Decision trees. Yeah, same thing. It's the same data set we are using because we need to check the accuracy and performance of the system. So we are going to use the same values. Same process. We are going to import the libraries. We are going to import the data set. We are going to split the data set, and we are going to feature scale the data set. Yeah, it's done. So okay, I'll just run it. But remember the percentage. The first logistic regression was 89, KNN was 93, and we'll check our decision tree. Okay, till here we are going to do it. Okay, so how the decision tree is going to split the trees, split the entire data points is by using entropy. So entropy is nothing but the amount of information situated at a particular point. Again, random state is used to no need to change. I mean, not to change the values every time whenever you're running the code. So in order to make the value static, we are using the random state. Okay, now applying the decision tree, yeah, it's done. And if I apply the prediction part, yeah, it's done. And I'm going to apply my confusion matrix. I'm going to apply my confusion matrix. Yeah, so I applied my confusion matrix. And if I check CM, it's 62 plus 29. Okay, the total values is always same, right? Since we are using the same data set and we are applying 25% of our test set. So total, it's 100 data points. So out of 100 data points, 62 plus 29 is my actual values are equal to the predicted values. So that is 91. 91 is also a good percentage. So that means, okay, see. Okay, that means logistic regression has given us a percentage of 0.89. And for KNN classifier, it has given us a percentage of 0.93. And now we have applied decision trees, and it has given us an accuracy of 0.91. So we'll see which model is giving us better accurate results. We'll look for that particular data set and we'll finalize that model. Okay, so if you apply the same the visualization techniques on the decision tree, it's the same thing. So the plots have everything. See, but the decision tree divides that into splits, right? Previously it was only one diagonal one, but here you see. So the complex algorithm. So how many splits you are going to do? That many splits are going to happen in this. So category 1 and category. That means if any data points falls under this red region, that belongs to the red category. If any data point falls under this green region, it belongs to that category. So this is very good, right? I mean, like compared to the previous algorithms, if you observe, so it's clearly, it is like creating layers inside a plane, on the plane. Like the red categories, belongs to somewhere else. So previously in the KNN, you might have seen like in the green data points also, some of the data points are going into that. But here you see, so it is creating layers kind of inside the test set directly. And it is able to predict the outcome. Suppose if any green data point is coming in this region, it automatically goes as a red data point. Yeah. So that's how, the decision trees work. The decision trees work with the splitting techniques, and it splits everything and it gives you the better results. Okay. Yeah. So decision tree. Yeah, we are good with decision trees now. So the one more technique what we are going to see in the classification is random forest. Okay. As we already know that random forest is an ensemble method. That means more than one algorithm, the machine learning algorithm is applied on the, not only machine learning algorithm, if you take any algorithm also, those are called as ensemble methods. Okay. Yeah. So more than one algorithm is applied on the to create the algo and all. So that's why it is called as an ensemble method. Ensemble methods always give you better results actually. I mean, like if you apply one or more algorithms on complex data sets, then it gives you a better results actually. Okay, let us see about the random forest. Okay, so same thing, but here the process will change. So pick at random k data points from the data set, training set. Like we'll pick some random data points, we'll build a decision tree associated to these k data points. And then we'll apply number of trees to it. Like we'll apply 10 or 20 or 30, it's up to us. Like randomly we'll check which is the best suited decision trees, number of decision trees for that particular model. We'll stick with that and we'll predict the results. Okay. For a new data point, make each one of your entries predict the category to which data point belongs and assign the new data point to the category that wins the majority vote. Right. Suppose if you're applying 10 trees, take an example. If you're applying 10 trees, see, understand the logic behind the decision trees. Okay. So after applying the decision tree, also random forest, it is taking the average of all the kind of average. So if you're going with regression, it takes the average. If you're going with classification, same, like in the k nearest neighbors, you have the majority votes, right? For example, you have 3 red data points in k and 2 data points in green. So that means 3 red data points are in the majority, 3 data points are more in the red category. So the new data point belongs to that. In the same way, here one decision tree will give you one prediction, and the second decision tree will be giving you the second prediction, and so on till n predictions. So out of all, like how many has given you, like for example, the first decision tree has given you that the new data point belongs to red category, and the second decision tree has given you that the new data point belong to the green category, and so on. So majority, you count the number of red data points and green data points out of all the decision trees. Automatically, the majority, whatever it has, it throws you that into that particular category. So that's how the random forest technique works.
Sir, second step once you can explain, sir.
Okay, I'll explain. Okay, see, it's very simple. So we will decision trees, we already know like how the decision tree is working. It is working by splitting the data and through entropy, the amount of information, the maximum information where it is able to identify in a particular group. So it is assigning that as a split. And then if a new data point is coming in picture, then that new data point is assigned to that particular group. That's how the decision trees work, right? Yeah, suppose, think like this. So there's a new data point and the first decision tree. So apply like 10 to 15 decision trees in the random forest. Okay, there's a new data point in the plane, and the first decision tree has predicted that the new data point belongs to red category. Okay, think like this. I have the first decision tree has given me red category, and the second decision tree has given you green category. Okay, third has given you red category again. Fourth has given you green category. Okay, fifth has given you red again. Six has given you green. 7 red, 8 green again. 9 red, 10 green again. So 11th decision tree, take one more decision tree. 11th decision tree, if it's giving you red category, that means in total we have 6 red categories and 5 green categories. I mean the prediction part. So the majority is 6, right? So that random forest will vote for the majority. So it takes and it considers that the new value, whatever it is there in the plane, belongs to the red category. So that's how the random forest technique works. Is that clear? I hope it's clear. So first we have seen logistic and then KNN and then decision tree classification. Okay, we'll go with random forest technique. Random forest classifier. Classification. Good. So we have this random forest classification technique, and we have our social network ads, same data set available. So again, we'll start from the basics. Good. So importing NumPy as NP, importing Matplotlib as PLT, social network ads we have. I'm going to choose X and Y, and I'm going to split the data set and scale, standardize my data set. Okay, I need to change this. Yeah, after standardizing, I'm going to import my random forest classifier. See, remember for the decision tree, you have this criterion as entropy, random state also, but the extra feature in the random forest classifier, what you're going to use, n estimators as 10. Okay, remember guys, since we have already learned functions, if you remember in the functions and the classes, we can have n number of parameters available, but the parameters which are very important only we are considering here. So there's so many parameters for random forest classifier, you need to explore those random forest classifier parameters in the documentation. So whenever you require those parameters, you need to use it. But for now, those are not required. So we are using only these parameters from the random forest classifier. It's very easy only. It's the same process for each and every algorithm, but understand which is giving a better accurate model. Okay, I'm going to predict the outcomes again. Good. And then I'm going to create my confusion matrix. Okay, I'll go with my CMs and see it's 63 plus 28. Let's see. 91. So the decision tree algorithm and the random forest classification is giving us same results. Like the accuracy, the percentage, it is giving us same results, that is 91% and 9% error rate. Okay, let us write it down here. Hashtag random forest classifier. It is giving us 0.91. So we'll remove the, what do we say, the points, and we'll write down the percentages. Okay, logistic regressor, that is 91, sorry, 89, right? 89. And we have a error rate of 11%. And KNN we have 93, and we have an error rate of 7%. This is good. Yeah. And in the decision trees we have 91, and we have this 9. And same thing. Okay. Sometimes see 93% of accuracy it might give you, but there's a chance that machine might learn more. Like machine might learn the patterns more. I mean more and more. Like it goes into a overfitting state. Okay, whenever this overfitting state is there, then the predictions or whatever, it gives you the accuracy of the prediction part. Whenever you are doing with a new data point, it doesn't give you that good results actually. So if it is not learning more, if it is not learning in a perfect way, then it might go into underfitting state as well. Okay, it will affect our accuracy actually, and it increases the error rate. So at that time, it's better to avoid that algorithm. And you can go with decision trees or random forest. If you feel that KNN classifier with good accuracy is not performing well in the later stages, then you can go with decision trees or random classifier also. That's up to us. Yeah. So now we have one more algorithm which is called a support vector classifier. So with this thing we have already seen in our SV regressions, support vector regression, and these two belongs to support vector machines. Okay, we are going to see the one more algorithm is there, and tomorrow we'll see the tile vector. Yeah, SVMs were initially developed in 1960s. Yeah, remember guys, whatever the algorithms we are looking at, these have been already developed by the statisticians and mathematicians long back only. Okay, we are just using it in a practical way, and we are deploying that by using technologies and all now these days. Clear? Yeah. So SVMs were initially developed in 1960s, and they were found again in 1990s. Now they're becoming popular. They're very powerful compared with other ML algos. Okay. So why? Why? Because see, if this is the case, so think like how can you divide these into categories? You can divide these into like multiple lines here. If you draw a line here diagonally, if you draw a line here like this, there can be multiple lines there. Okay, see, now we'll try to separate these categories with lines, and we are in confusion which line suits better, right? We don't know which line suits better. Till here, we have seen all the decision boundaries for different algos we have built. One way is to draw a vertical line in the 2D space. Okay, like this. One way is to draw a vertical line in the 2D space where you can divide the categories actually. So, but what is the issue if you draw like this? Anything to the right will be green. That's right. Anything to the right will be green, and anything to the left will be red. Now we know to which category we need to assign a new data point, right? However, now we can draw a horizontal line too. Choosing a boundary is difficult. Which better fits the algo, right? We don't know which line best suits. Lots of different lines we can create like this. So how SVM select this boundary line? SVM selects a line which is called as maximum margin. Okay, maximum margin is drawn based on the equidistance factor. See, so this is called as maximum margin. This is a maximum margin. So think like this. This is the data point of the red. So this is the last data point, and this is the last data point for the green. So if you draw a distance between these two, if the distance is equal, then it decides that boundary line actually. And these are called as support vectors. That's why it is called as support vector machine algos. Right? Okay. See, now the line in the center is called as maximum margin classifier in 2D space and minimum margin hyperplane in a 2D space. Maximum margin hyperplane. Sorry. So, yeah. So if you see the lines here, so this is called as positive hyperplane, and this is called as the maximum. This is the center point is the maximum margin, and this is the negative hyperplane. That means the values which lie below this hyperplane belongs to red category. The values above this positive hyperplane belongs to the green category. Right? Imagine that we are training a data that contains apple or orange data set. If I give a new fruit, it tells me the category. For example, see, we have apples and we have oranges. Right? Based upon the equidistance factor and all, it decides. But what happens if you see, this is an apple, right? But what happens if the machine thinks that is an orange? Because we are training the machine with this kind of colors and all, with this color kind of. So, but what SVM does is it neatly assigns itself. It neatly understands each and every feature of it. And then it gives you the better result, better output actually. Okay, when you're applying for larger data sets like this kind of things, no? So then you can go with SVMs. Okay, we'll check our SVM data set as well. Okay. Support vector machines. Good. It's the same data set again. So since we are going to check the accuracy of the models, okay, we'll start from scratch. Okay, good. So now I'll take it here and I'll apply this. Yeah. Since what is the kernel you need to apply that, whether you are going to apply the linear filter kind of, you need to go with linear. So there are different kernels actually, RBF filters. There are so many filters out there. But for this, we are going to use only linear. Since this is a small data set and linearity is good. So because, yeah, linear curves are fine with the data set which we are using. I'm just directly applying the prediction part and then the confusion matrix. I will CCM 66 and 24. 66 and 24. See the beauty. SVMs 66 plus 24. 90. This is 90%. That's cool. Fine. Yeah, go here and we'll just type SVMs as 90% and 10% the error rate. So now see, so the like different algos have different accuracy percentages, and we need to choose the best algo out of this. So 93 being the 93% KNN classifier, that doesn't mean it gives you the better predicted results after when you supply data points or something. But after vigorous tests and all, no, we are like applying only one test. We have taken some random sample, and we have applied one random test on it. But you need to like create at least 5 to 6 samples and 5 to 6 tests, and then you decide which algorithm is best suited for it. For that, we use this randomized CV search or yeah, forgot the other name. Yeah, so kind of there are some techniques where you can use it and you can perform grid search. The other one is the grid search actually. Okay, so now we have these many algorithms and we have these many accuracies. So KNN is performing good, so we'll decide that KNN is the best suited algorithm so far. So far, it is the best suited algorithm, and then we are going to use it. Yeah. So I guess, yeah, that's it for today, guys. Like, go through the regression data set which Hyse is going to share with you. Regression techniques, the coding part and all. I'll adjust the